In this video, we'll explain how the properties of the exterior derivative serve to define it uniquely. So in the previous video, we gave you a formula for the exterior derivative. So we got a formula for d using coordinates, and this, one of the properties, one of the four characterizing properties is part of the formula, and then the formula implied these three properties. And in this video, we're going to show that, in fact, if I want some operator satisfying the three properties, and to sort of extend D on functions, it has to be given by the formula of the previous video. So the reason why we do this is there are a number of different objects in mathematics that are defined in this way, which is called defining something axiomatically. So basically, you define an object through its properties and then prove that such an object exists and is unique. And often, the method that you use actually derives a formula or some kind of closed description of the object. So it's sort of giving you like the motivation for what you would want the object to do, and then sort of solving for what it has to be secondly. So right now what we're going to do is assume that we basically haven't seen everything we saw in the previous video. So we're going to try and prove that if I want D to satisfy the three properties, then it has to be the D of the previous video. So the theorem is there is a unique operator D, which goes from K forms on any manifold to K plus 1 forms on that manifold, and we call it the exterior derivative, satisfying the following properties. So if I take D of two forms, if the sum of two forms, then I get the sum of the D's of those two forms. If I take D of a wedge product, then I get the wedge product of D alpha with omega plus -1 to the K alpha wedge D omega. So here, alpha and beta are both K forms. Here, alpha is a K form, and omega is an L form, any other form. And then the third property I want it to satisfy is I want D squared of alpha to be 0. So when I apply D twice, I get 0. And then usually I would write this without any. So in your book, Fortney usually writes this. I can also write, I also will often write this, D squared is 0. And then in local coordinates, if f is a function from m to r, then df equals the sum from I equals 1 to n, where n is the dimension of the manifold, df dxi times the one form dxi. So we're going to prove that if such an operator exists, then it is unique and it has to be D. And we'll do that just by finding the formula for D using this method. So remember, if I want to apply D to some one form, some K form, all K forms can be written the sum over I, where I is a tuple of K coordinates between 1 and n, and I write them in increasing order, and A sub I is a function. So so what I need to do is I need to show that this formula is equal to the formula I got. I had in the previous video. So when I apply this, well, because of property 1, I want to have this, I can put the d inside the sum. So I can do the sum instead outside. And then because of the formula for, so basically I'm thinking of multiplying by a function as the same thing as taking a wedge product with a 0 form. That's basically the same thing. So it's, yeah, so what I would note here is that if you go back through sort of what it means to define the wedge product of 0 forms would just be multiplication. So ai dxi, I can also write as ai wedge dxi. And then using this convention, I can use the second property. So I get the sum over I dai wedge dxi plus -1 to the 0 ai d dxi. And maybe it's a little bit confusing to write it this way because it sort of looks like d dxi is d of a function xi. So I'll write it as dxi1 wedge all the way out to dxik. Okay, so now what I'm going to do is write is sort of take this second property and apply it multiple times. So this is just by applying property 2 again and again. I'll get the sum over I dai wedge dxi. -1 to the 0 is just 1. And then this will be ai times dxi1 wedge all the way out to dxik plus, so these are now, so there'll now be some alternating signs. So these are all 1 forms, right? So these will be -1 to the 1, dxi I1. Actually, here above here, I should add maybe something else just so we sort of know exactly what's going on. dxi2 wedge, okay? And then I will be computing now d of dxi2 wedge all the way out to dxik. And there should be another parentheses. Okay, so essentially what's going to happen is in this term, right? So this term is 0 by property 3 because d xi is the derivative of the coordinate function xi. And hopefully you'll believe me that similarly every term in here in d of dxi1, dxi2 wedge all the way out to dxik will also be 0 because I'll again be multiplying by the first term, which will always be 0. So I'm going to be left with, by property 3, the sum over I dai wedge dxi. And then this is exactly the formula that I mentioned in the previous video of how to compute the d of a general form. So we're not quite done. So what we really should do next is prove that this formula satisfies the properties. But that is what you're going to do on your homework. We've already done the first one. We've done this one. So what you have to do on your homework is these two. And so the reason why you would define D this way instead of using coordinates is that it's sort of unclear that the definition of D doesn't depend on the coordinates you've chosen. And so this makes it a little bit less dependent on the coordinates, but we still have this sort of coordinate issue. So in the next video, we're going to discuss how to define D without using any coordinates at all.